Good day, everyone. And we have to proceed, no? A continuation of our discussion in a thin-walled cylinder. So this is another example. Now, suppose you are given a water tank having a diameter of 8 meters and a height of 12 meters. If the tank is to be filled completely with water, determine the minimum thickness of the tank plating if the stress is limited to 40 megapascal. Okay, see, your tank looks like this. No? So this is filled with water completely. So these are the dimensions. Then you are required to solve for the thickness. And there is an allowable stress of the tank plating which can be less than or equal to 40 megapascal. Now, we already know that the tangential stress is more critical compared to the longitudinal stress, no? So, I can go directly to the tangential stress as my consideration. Okay? Now, in the formula for the tangential stress in a thin-walled cylinder, the formula is rho d over 2t for the tangential stress, and that is rho d over 4t when that is the longitudinal stress. While I have a value for this, now because it's t that is required, this one is part of the given. Ang imuhang d is also given, but pure pressure is not directly given, but it only mentions that the tank is filled with water. So what is the pressure caused by water inside the tank or inside your cylinder? So, the formula for pressure inside the tank, if we assume that there is a uniform pressure distribution, is actually a product of the unit weight of water times the height h. So, in our given, by the way, the unit weight of water is 9.81 kilonewton per cubic meter, or in English unit, that is 62.4 pounds per cubic foot. So, I multiply this with the height. The height, this one, this is your pressure head, no? And that is equal to 12 meters. So, that can be a unit of kilonewton as I reduce the exponent of my m to square. So, this is kilonewton per square meter. Actually, this can also be a unit in kilopascal. So, I have a value, 117.72 kilopascal. If you want to express your unit in terms of megapascal, so I have to show a sample conversion. So, you have the pressure. That is 117.72 kilopascal. That is good as, the kilo is good as 1,000. So, that is multiplied with 1,000. The unit is now pascal. Now, if I want to express that in terms of megapascal, 1 megapascal is 10 to power 6. This is 10 to power 6 Pascal. So, Pascal is out. Then, this is the equivalent value. So, kilopascal, you just move 3 decimal places going left. And that is already a unit in megapascal. Okay, megapascal and megapascal, we also know that that is Newton per square millimeter. Okay, so equivalent to that. So, after knowing the pressure, and I have to assume that there is a uniform pressure distribution, so I can now use the formula. Okay? The formula we derive for the tangential. So, this one has a given value, 40 megapascal. So, if this is in megapascal, then it would be good to express my pressure also in megapascal. So, megapascal equivalent for that. And my diameter, okay, let's substitute. I have 40 megapascal. In megapascal, my pressure is this one. So that my T unit will be dependent on the diameter. Megapascal is eliminated. The unit for T is expected to be the same unit as your diameter. That is in meter. So in meter, then, I can convert that to millimeter by multiplying with 1,000. Now, if I'm going to solve the thickness using the longitudinal stress, actually, you can even consider half of this as the thickness. But since we say that our tangential stress is critical, then I can use this as my governing thickness to make it safe for both longitudinal and the tangential. But maybe, if you have knowledge, this is already the answer, But if you have knowledge in dealing with hydrostatic pressure, no? Okay. So, my hydrostatic force, no? Which is this one. Actually, the pressure here is not actually uniformly distributed. As you notice, no, so that is increasing linearly as there is a variation of the height edge. No, it increases from 0 to a value. So in this is h, so that is unit weight times h. So that is the pressure diagram. The total hydrostatic force F, which may cause bursting later, no, of the container if that is so excessive. So your F is equal to the volume of your pressure diagram. Okay, what is the volume of your pressure diagram? Okay, so by the way, the solution, no, is not the application of the formula we introduced. Only I have to show lang that there is also a different approach in dealing with problem like this. Okay? So what is the volume? Area for the side is triangular. 1/2 base and height. 1/2 base is the product of unit weight times h, then multiply the height h, then this one, diameter, to have the volume. So you can multiply h squared or h, and that becomes h squared, and then we can substitute the values. 1/2, 9.81 kilonewton per cubic meter. This is 12 meter in square. Then we have a diameter of it. This will give you a value which is in kilonewton. This is your hydrostatic force, F, which is your bursting force. That bursting force will be resisted by these forces. This is the resisting force. Okay? What's the relationship between P and F? Okay, so we're not going to use directly the formula, so rho d over 2t, but instead, we analyze the relationships of these forces, the bursting and the resisting. Okay? So this is my diagram. Actually, the diagram is taken from this, no? So I have 2p, which is this one, and I have my bursting force. To get the relationships, I may take the moment at point O. By the way, since this is triangular, my force F is acting at a height of 1/3 of the altitude h. No? And then, my 2p is exactly halfway. So if this is 12, this is 6. And if this is 12, 1/3 of that, so this is 4 meters. Okay? Now, taking moment where I already have the value of F. Okay? So, if I have to take moment at O, my 2p has a distance or a moment arm of 6, no? And that is clockwise rotation. I have a counterclockwise moment of F, no? So, F times a distance of 4. So, I have to reduce by dividing with 4. So, this is 12 divided by 4. I have 3p equal to F. So, my P is 1/3 of F. And if you get the value of your P, my P is equal to, okay, I arrive at the value. Now, P in relation to the allowable stress and resisting area. So, it's a product of allowable stress and the resisting area. So, I can now substitute values. Okay? So, take note that we will be solving for T. This is the force F, P, wherein the value is already there. That's kilonewton. I express that in terms of Newton by multiplying with 1,000. So, this is Newton per square millimeter, 40. And this is 12. This is in millimeter. So, I can express my height in terms of millimeter. So, 12 meter is 12,000 millimeter. So, there I have the unknown thickness. Reducing this and out atong in. So, there I have a unit for T, which is in millimeter. So, take the difference of the value we obtained kanina. We obtained a value, a safe thickness, which is 11 point something, while karon, we were able to show that a thickness of 3.924 is even safe now for this container. Now, actually, if you are a designer, so you also have the option to look for a design wherein the cost is considered. So, kung mag-design gani ka, so you also have to consider cost, and safety of your design. So, but this value of T is not based on the formula we are using. Because in our formula, the assumption there is a uniform pressure distribution. So, talking with answer, so that answer 11 point something is the one which will be used. But if you will be a designer, pohon, then you can have the option of using a thickness which is even lesser than that one. And you can prove that this answer is still safe for your cylinder. Okay? So, this time, no, you are only given the option on what thickness are you going to use. But, for now, just limit your approach, no? And the formula we are using for cylinder, the rho d over 2t and the rho d over 4t for the longitudinal stress. Another kind of container is a spherical tank. A wall thickness of a 4 feet diameter spherical tank is 3/8 of an inch. Calculate the internal pressure if the stress is limited to 8,000 psi, pounds per square inch. Okay? Now, this is how it looks, no? A sample of a spherical tank. Okay? Then, we are required to determine the internal pressure with given data. Thickness is 3/8 of an inch, diameter is 3 feet, no? Then, allowable stress is 8,000 psi. So, it looks like this, no? If I have to pass a cutting section, right half of the cylinder at half of the cylinder, and I form, half of the spherical tank, and I form here a hemisphere, no? Now, this is the area at which the pressure will be acting. So, if that is projected here, so this is the area at which the pressure of the fluid inside the container will be acting. So, that is if will be acting. And your P is actually the resultant of all these forces which will resist the bursting force. The bursting force is due to the fluid pressure inside the spherical tank. At equilibrium condition, obviously, you will notice that your F and P are equal. Resisting is equal to the bursting force. By the way, some figure of that same nature, no? So, there may be relationships that you have to consider. Like, the DO is the outside diameter, which is this one. In relation to the inside diameter, which is kina. So, in your figure, the outside diameter is equal to D, the inside diameter, plus. If this is T here, then there's also another T there. That is why inside diameter is added with 2T. That is the outside diameter. Figure again, it looks like that. No? So, whenever this is needed, maybe in your activity or in your quiz, no? So, do not forget these relationships or this figure. Okay, let us proceed with the equation we obtain, wherein we say that our resisting force, force P is equal to the bursting force F. Okay? So again, my figure is like that. P is equal to F. And what is P? That is the resisting. The resisting depends on the allowable stress of the material used. So it is stress times the area, resisting area. While this one is the force, is the pressure that is acting on the area. So I have the stress which is equal, which is multiplied with the resisting area. Being a thin-walled container or a vessel, the circumference being a circle manila, is having a formula of pi d. Then simply multiply your circumference with the thickness. So this is the resisting area. Then pressure, okay, so this is not part of the notation. The correct notation for pressure is simply this one. Area is the area of your circular section. No, this is the area at which the fluid pressure is acting. So pi d squared over 4. Now, when you have to simplify, my pi can be removed as common on both sides, no? And I can go with reduction of my d squared to d after removing this. So if I have to define what is the stress on the spherical tank, what is left is pressure times d here over 4, but I have t here. So coincidentally, we arrive with a formula for spherical tank which is almost the same, which is the same as it looks in the longitudinal. But this is not a longitudinal stress because there is no link considered in spherical tank. So, maulit siya, yung formula. So, this is exclusively used also for the spherical tank. And after knowing this formula, so I can proceed with the substitution of the given. The allowable stress is given as 8,000 psi. We are required to give the internal pressure. So, my internal pressure unit will depend on the unit of the stress. If this is rho and D and the thickness must bear the same unit to eliminate the unit for the ratio. So, if this is in inches or inch, this is in feet, so feet will be converted to inches. Or say, my inch unit will be converted in terms of foot. No? So, kinina lang. 4 feet is equal to 12 is converted to inches. So, we have a conversion factor 12 inches per foot. No? So, foot is out, inches is out, and then we have a unit of psi left, and that is the value of your internal pressure. So, we simply take the relationships from figure, and we were able to arrive at the formula. So, I tried to derive the formula because whenever you can encounter problem involving spherical tank, then this formula may be used directly rather than having like a derivation of formula. Okay, so, but if you fail to recall the formula, then just have the relationships of the allowable, of the resisting force with the bursting force. So, you can still arrive with the answer. Okay, so that is the end of the thin-walled vessel or a thin-walled cylinder problem. No? Okay, so thank you and bye-bye.